Welcome to Naming Simple Compounds. So first we're going to look at binary compounds. Now bi means two, so binary compounds are composed of just two elements. Not necessarily two atoms, but two different elements. So they may be composed of more than two atoms, but of only two types. So we have methane, CH4. Again, we've got 5 atoms, but only 2 types, carbon and hydrogen. We've got sodium chloride and water. So first we'll look at the ionic compounds. So binary ionic compounds are ionic compounds that contain 2 ionically bonded elements. So this is something like sodium chloride or iron oxide or potassium fluoride. So if the binary ionic compound contains a cation of an element with only one possible positive charge, so this is groups 1, group 2, group 3, and aluminum, zinc, and cadmium. If our cation is from one of those elements, or from one of those groups, then our cation is named first and our anion second. A monoatomic cation name is the name of the element. So if we have, say, aluminum, the cation name is aluminum. If we have, say, a sodium ion, it's just sodium. We don't change the name of the element at all for a cation if it's monoatomic. So a monoatomic anion name is the root of the element name plus the suffix IDE. So if we have, say, chlorine, we have the root chlor plus the suffix IDE. So that becomes chloride. Oxygen, we take the ox part, that becomes oxide. Carbon becomes carbide, and so on. So here we have NaCl. Well, we name our cation. The cation is the positively charged one. That will be the metal. It's always the one listed first on the left. So we have sodium and chlorine. Chlor is the root, so that becomes chloride. BaF2 is barium fluoride. Li2O is lithium oxide. Al2S3 is aluminum sulfide. K3P is potassium phosphide. Now note that in none of these cases do we list anything about how many, right? So we've got the numbers here in the chemical formula, but we don't have any numbers in our name. And that's because we don't need them in our name as long as we know what the charge is on each of these, we can figure out how many we need. Because if we know that, say, sodium has a charge of +1, and chlorine has a charge of -1, well, to balance out the +1, we need just a single -1. So the number on each one of those is 1. With barium, if we have a charge of +2, 2+, and fluorine has a charge of -1, well, we need 2 -1 charges to balance out the +2 charge. So we need 2 fluorines for each 1 barium. And so on. We can go on down. Aluminum has a charge of 3+, sulfur has a charge of 2-. So the only way we can get those to balance is by having 2 aluminums for a total charge of 6+, 2 times 3+, and 3 sulfurs, because sulfur has a charge of -2, and so we need 3 -2 charges to balance out the 2 +3 charges. So we can do that. So we don't need to write down how many of each atom we have, because we can figure it out just knowing what the 2 ions are. Now, you may need to memorize the roots of the common ions, but you're in luck because the common ions, the anions rather, well, the only ones we need to look at are the nonmetals and the metalloids to a certain extent. And so we have hydrogen, that becomes hydride. Helium, well, that's a noble gas, that won't form an anion. So we can ignore all of these guys. We have boron, that becomes boride. Carbon becomes carbide. Nitrogen becomes nitride. Oxygen becomes oxide. Fluorine becomes fluoride. Silicon becomes silicide. Phosphorus becomes phosphide. Sulfur becomes sulfide. Chlorine becomes chloride. Germanium, I don't know what that is. I've never used it, so you probably don't need to know it. Arsenic becomes arsenide, selenium becomes selenide, bromine becomes bromide, antimony would be antimonide, tellurium would be telluride, iodine becomes iodide, polonium would be polonide, acetine is acetide. So, those are the only ones that you need to know. All of the other ones are metals. Those will be positively charged cations, so you don't need to know the roots of them. So, if the binary ionic compound contains a cation of an element with more than one possible positive charge, so these are the transition metals, the inner transition metals, so the lanthanides and actinides, and the metals that are in groups 13 to 16, so this is the p block metals. So in this case, you need to name the compound as above, so you name the cation, name the anion, but you need to add the oxidation state of the cation, written in Roman numerals, in parentheses, after the cation name. So let's look at some examples. Or also, there was an older way of naming some of these compounds, which was to use the root of the cation plus a suffix. The suffix was "ic" for the ion with a higher charge, a higher positive charge, and "us" for the ion with the lower charge. So in this case, we have Fe2O3. We know that oxygen has a charge of -2. That means that the iron has a charge of +3. So we write that the standard way is iron 3 oxide. Again, this 3 is in Roman numerals in parentheses. And the old name for that was ferric oxide. So you may see some bottles of chemicals labeled with this name if it's an older bottle, or you may see something labeled with both of them. You may see some laboratory procedures with some of the older names in there as well. FeO, oxygen again oxide has a charge of -2. If we only have one of each, that means that the iron has to have a charge of +2. So there we have iron 2 oxide. That would have been called ferrous oxide. If we have some case like this, we have tin 2 chloride. Again, the chloride has a charge of -1. So the tin there, because we have 2 chlorides, tin has a charge of +2. So this is tin 2 chloride, or stannous chloride. Here we have 4 chlorines, so that means the charge on tin is +4. So we have tin 4 chloride, or stannic chloride. So a polyatomic ion is an ion containing more than one atom. We've already talked about this a little bit. So the charge of a polyatomic ion is for the entire group of atoms. It's not on any one particular atom, or it may not be on any one particular atom. So the group of atoms is covalently bonded together, but it's not a molecule because it has a charge on it. So it's a polyatomic ion. So here we have table 3.5 from the Zumdahl book. This is on page 129 in the first edition. So here we have a listing of all of the common polyatomic ions. I'm not going to go through all of them. You should look through the book. For these guys, for the most part, you're just going to have to memorize what they are. You should know basically all of them. I'll point out a few of them. Some of the really common ones are nitrate, sulfate, peroxide, cyanide, hydroxide. I want to point out here for this one, CO3 2-, that's carbonate. If we add a hydrogen to it, it's called hydrogen carbonate, or sometimes bicarbonate. This is one of the components in baking soda. Baking soda is sodium bicarbonate, so we have a carbonate with one hydrogen. That's where the bicarbonate comes from, and a sodium ion in there as well. Again, these polyatomic ions are special names that don't really have much of a system to them, so you really need to memorize what they are. Some of the related polyatomic ions can contain different numbers of oxygen atoms that have names ending in ITE or ITE for the ion with fewer oxygen atoms, or 8 for the ion with more oxygen atoms. If there are more than 2, then usually there are 4, in which case the one with the fewest oxygen atoms has the prefix hypo and the suffix ite. So for something like chlor 8 chlorite, we get hypochlorite. And the one with the most oxygen atoms is per blank 8. So per chlor 8. So in this case, ClO is hypochlorite, ClO2 is chlorite, ClO3 is chlor 8, ClO4 is perchlorate. So a compound containing an ionic compound is named using the name of the cation, whether it's monoatomic or polyatomic, plus the name of the anion, whether it's monoatomic or polyatomic. So, something like NaNO3, the Na is the cation, that's just a simple monoatomic cation, sodium. And the NO3, that's the nitrate anion, polyatomic anion, so this becomes sodium nitrate. NH4ClO2, that contains two polyatomic ions. One is the NH4 plus part, that's ammonium, and the other part is the ClO2 part, that's the chlorite part. So that covers ionic compounds, but now we get to binary covalent compounds. So these are compounds that contain two elements that are covalently bonded together. So the way we name these is the first element in the formula is named first, using the full element name. Just like for an ionic compound, we're not changing the full element name at all. The second element is named as if it were an anion, so that means with the suffix IDE. So we're pretending like it's an anion, even though it's not. And here, prefixes are used to denote the numbers of atoms present. So with the ionic compounds, we didn't have to list any prefixes. In fact, it's not appropriate to list what the prefix is. But in this case, we do need to list the prefixes for covalent compounds because we need to avoid, or in order to avoid awkward pronunciations, we drop the final O or A of a prefix if the element name begins with a vowel. So, if we have something like oxygen, if that becomes oxide, we don't say monooxide, we say monoxide, and we drop the O of the prefix. So the prefix mono is also not used for naming the first element, although it is used for the second element. So if we have something like CO, we would label that carbon monoxide. We wouldn't say monocarbon monooxide. This first one is nitrogen, N2O, that's dinitrogen monoxide. This also might be called nitrous oxide. NO is nitrogen monoxide, nitric oxide. Again, note that we're not listing the mono on nitrogen. And again, we're also cutting off we're dropping that O on mono for the monoxide. We're not dropping the O at the beginning of oxygen. We're dropping the O at the end of mono. So NO2 is nitrogen dioxide, N2O3 is dinitrogen trioxide, N2O4 is dinitrogen tetroxide, N2O5 is dinitrogen pentoxide. So I want to continue. If you go past 5, then you get to hex. 7 is hept, H-E-P-T. 8 is oct. 9 is non, N-O-N. 10 is dec, or deca. So some compounds are always referred to by their common names, not by their systematic names. So something like H2O would technically be dihydrogen monoxide, but we never call it that, we call it water. NH3 would technically be called nitrogen trihydride, but we never call it that, we call it ammonia. H2O2 is hydrogen peroxide, not dihydrogen dioxide, and this is because this peroxide, the O2 part, it implies something different is going on, because in this case the oxygen atoms there are acting like a polyatomic ion peroxide, which has a charge of 2- on the whole grouping of 2 of them. All right, so now let's get to naming acids. So if the acid does not contain oxygen, then if the name of the anion ends in IDE, then the acid is named with the prefix hydro and the suffix ic. So for something like HCl, the anion is chloride, that ends in IDE, so that becomes hydrochloric acid. HCN, the CN part is cyanide, that ends in IDE, so that becomes hydrocyanic acid. H2S, the S part is sulfide, so that gets named hydrosulfuric acid. So note that even though we've got two hydrogens there, we still don't have to put on a prefix there saying that we have two of them. It's not bihydrosulfuric acid or dihydrosulfuric acid. So if the acid does contain oxygen, then the acidic name is formed from the root name of the anion with a suffix of "ic" or "us", denoting whether we have more or fewer oxygen atoms in our polyatomic ion. So if the anion ends in, or an anion name ends in "ate", so something like sulfate, then a suffix "ic" is used. So this becomes, so sulfate in an acid form would be sulfuric acid. If the anion ends in "ite", then the suffix "us" is used. So H2SO3, so sulfite in acid form would be sulfurous acid. So let's look at the choroxide compounds. So HClO is hypochlorous acid, HClO2 is chlorous acid, HClO3 is chloric acid, HClO4 is perchloric acid. So here we have the names of the six, or of a few common acids that do not contain oxygen. Here we have the formulas and names of some of the acids that do contain oxygen, some of the common ones. So we have hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, hydrocyanic acid, hydrosulfuric acid. Over here we have nitric acid, nitrous acid, sulfuric acid, sulfurous acid, phosphoric acid, and acetic acid. So note here that we have a sulfuric acid, H2SO4, and also a hydrosulfuric acid, H2S. Right? But these are two very different compounds. I mean, they both contain sulfur, but other than that, they react fairly differently. So that was naming simple compounds.